is important. Wires inside walls. Different countries have different plugs for connecting devices to the mains, and the blue neutral wire carry the current around the circuit. The current is alternating current, which travels back and forth approximately 50 times a second. Appliance. Neutral wires have a voltage close to zero. Casings. If a loose wire touches the metal casing, anyone who touches the appliance will get an electric shock, which is where the earth wire comes in. The earth wire connects to the earth pin, which takes the current away from the appliance into the wiring of your house and down to the earth through the house. Much safer. Live and neutral pins. Therefore, whenever you plug in a plug, the earth pin always connects with the socket first. The fuse is a outer insulation of wires.
3-point plug, Phillips head screwdriver, flathead screwdriver, wire strippers, pliers. Remove the cap, remove the other screw and put it away safely. Pick up the plug for when you rewire. And now we're ready on the cable. Carefully snip the outer sheath as not to damage any of the internal cables, making sure there's an adequate amount of sheath for the cable clamp. First off, let's identify to let you know which cable goes where. Brown goes to the neutral. Green and yellow goes to the earth. Use the pliers to mark. We twist the copper wire until it's compressed. This ensures, if you need to, you can raise the terminal heads by pushing on the pin. Once you have the first wire inserted, screw tightly to close, ensuring that there's no exposed copper to provide ease of insertion. Although it's important to make sure there's no copper exposed, be sure not to plug head. This will ensure that your cap will go on snugly. That the screw is engaging in the thread by checking it as you screw. It could indicate that some of the internal wires are over the structure of the firmly in place.
Domestic electrical circuits, the size of conductors that are used in the circuits, as well as the size or rating of protective device. Every new circuit has to be designed by calculating the maximum load of the circuit, choosing the right size circuit breaker, and calculating the right size of the cable, by taking into account its length, method of installation, ambient temperature, voltage drop, and few other factors, and then the whole circuit should be tested. I'm not going to do any of these calculations in this video. Instead, I'd like to simply explain the construction of each circuit and what is the recommended size of cable and MCB for each one of these circuits. You can also find this information in a consumer unit, and we've got 4 socket outlets on this circuit. So the 2.5 twin-earth cable goes from consumer unit to the first socket outlet, and then from the first to the second, and so on, and it finishes at the last socket outlet. The MCB for this radial circuit should be 20 amp. Another commonly used circuit for socket outlets is a ring final circuit, or simply ring. So again, top right corner we've got the consumer unit with 32 amp MCB, and let's say we've got 6 socket outlets on this ring. 2.5 twin and earth cable from consumer unit goes to the first socket, then from socket to socket, and from last socket to the cable goes back to the consumer unit. The 2 brown live wires from both cables we connect to the same 32 amp MCB. If we want to make a spare from any of the socket outlets, Simply use 2.5 twin and earth, run to the spare socket, and that's it. If you need more spares after the first one, then between the ring and the first spare you need to install 13 amp fused connection unit, FCU. And then you can have that give us 3120 watts current. This has to be dedicated circuit straight from the consumer unit. So we've got 32 MCB at the consumer unit, then we need to run 6mm cable, 6mm twin and earth cable to the 45 amp cooker switch, located at least 30 cm from the hob, and from this switch we run the same 6mm cable to the cooker connection unit that is usually under the hob. And then with a flex resistant cable we wire the hob to cooker connection unit, RCD protected, as on the ceiling of the bathroom. Or if you don't like the pull core switches, you can have wall mounted 45 amp switch. The MCB depends on MCB. Ideal, they start at the consumer unit and finish at the last point. Usually 1 mil cable and 6 amp MCB is enough for domestic installations, unless you've got really long circuit. Then 1.5 cable and 10 amp MCB. There are 3 methods of how you can run the lighting circuit. Unlike the power circuits, the lighting circuits are more complex, as the cable not only goes from light to light, but also need to be split at some point to fit the switch in every lamp location. The first one is called a loop-in method, and you can see it on this picture. Every ceiling rows, the live wire split to fit the switch. Got 3 lamps, not necessarily with the ceiling rows, 3 switches for each lamp, and 3 junction boxes somewhere inside the ceiling. Each of these junction boxes work like the previous ceiling rows, and the live wire from the switch is fit from there. In both of the systems you have only live wire at the switch, not the neutral, then from switch to switch, and the point where you split the cables is at the switch. Obviously it requires a deeper back box to accommodate all the wires and connectors, but the advantage of the system is that you don't need to use a stepladder if something goes wrong, as all the connections are at the switch. Or if you want to install a smart home switches
generated far away at the power station. The electricity leaves the power station and the voltage is increased in a step-up transformer, where it will then be distributed over long-distance transmission lines. We generate and distribute AC alternating current because it is more efficient and convenient than DC direct current. Once it reaches the town, the voltage will be reduced in a substation step-down transformer. From the substation, the electricity will either be distributed locally through overhead or underground cables. Depending on the local design and the voltages being used, a home might be connected directly to a small transformer located close to the property, or alternatively, a group of houses will share a larger transformer. Now, each house in a street might be alternately connected to a different phase, or different streets might be connected to different phases. This is just to try and balance the demand on the transformer. A smaller service cable comes off the distribution cable and will feed the property. This service cable will again be overhead or underground depending on the local installation. The service cable contains the phase and neutral wires. There's also a metal protective sheath around the cable in most cases, especially if it's buried underground. The service cable comes in, the electricity is going to flow through the phase, pass through the main fuse, then through the electricity meter and then into the consumer unit. The service head or cutout holds the main fuse or service fuse. This fuse provides protection to the property and ensures only a set amount of current can flow into the property. For example, in the UK it's typical to have a fuse rated between 60 and 100 amps. The consumer unit or fuse board varies in size depending on the size of the property and how many circuits there are being controlled. Inside the consumer unit we first have the main switch or main double pole isolation switch. This controls the supply of electricity to the rest of the consumer unit and therefore all the circuits feeding the property. This switch is not automatic and must be manually flipped to cut the power. This switch will disconnect both the phase and the neutral line together. The cables typically enter the main switch via the top terminals. At the bottom we find the neutral wire, which will connect to the neutral block connection. We might find one or more phase wires coming out of the bottom of the main switch to feed the RCDs. If there aren't RCDs being used, then a bus bar will feed the circuit breakers, but we'll look at that again shortly. The phase line enters the RCD or residual current device, again usually entering via the top. This RCD switch is constantly monitoring the electrical current. It's checking if the current in the phase line is equal to the current in the neutral line. If you touch a live wire and electricity flows through you to the ground, then the current is bypassing the neutral wire, so the phase and the neutral currents will not be equal. The RCD will notice this and then cut the circuit to reduce the risk of electric shock or death. It's now increasingly common to have 2 or more RCDs in a consumer unit. In such case, the RCD will only cut the power to the circuits connected directly after it. The busbar. This is just some conductive metal which the electricity flows along and connects into each of the MCBs, which just makes the installation easier rather than having a lot of cables. The MCB or miniature circuit breaker controls individual smaller circuits. For example, connected to one RCD, maybe we'll have one MCB for the downstairs lighting, one for the upstairs lighting, and one for the kitchen plug sockets. On the other RCD, maybe we have one for the stairwell lighting, one for the upstairs lighting, and one for the downstairs plug sockets. The MCB is rated to handle a certain amount of current passing through it, for example 32 amps for the plug sockets. If this value is exceeded on that circuit, for example by gradually plugging in too many things, then the MCB will trip and cut the power to protect itself. The other protection it offers is short circuit protection. In the event of a short circuit, for example the live touches the neutral, then the circuit is bypassed and there may be a large and instantaneous increase in current. This will create a magnetic field inside the MCB which will cut the power to protect itself.